In this video I want to talk about parallelism. So even though I'm not going to go into very much detail on the different types of parallel processes, but it is a natural extension of what we have discussed for sequential logic circuits. So generally speaking, there are two types of parallelism. We have the spatial parallelism, which basically means that if we have duplicate hardware, we can perform multiple tasks at once. And then we can have the temporal parallelism, which basically means that we either can break down a task into multiple stages. It is also called like pipelining. So for example, in an assembly line we have an example of a temporal parallelism. So let's just go over a few definitions that are commonly used in parallelism. First, we have the definition of token, which is representative of a group of inputs that are processed to produce some groups of outputs. So this is what is called as a token. We have latency, which is the time that it takes for one token to pass from start to end. And then finally we have throughput, which is the number of tokens that are produced per unit of time. So this unit of time can be anything. So it can be second, minute, hours, depends on the context. So the whole point of parallelism is to increase throughput. So even though the latency might stay the same for each token, but the final goal is that we increase the throughput or the number of tokens that are produced per unit of time. So let's just go over a very basic example and see how using different types of parallelism can help us increase throughput. So Ben wants to bake some cookies to celebrate his traffic light design, an example that we have seen before. So for these cookies, 5 minutes it takes to roll the cookies and 15 minutes it takes to bake the cookies. Now the question is that what is the latency and throughput without having any parallelism? So if you remember, the latency was the total amount of time that it takes for each token to go from start to finish. For us here, our tokens are cookies, so it takes 5 minutes to roll and 15 minutes to bake. So that means that the latency for each batch of cookies equals 5 plus 15 or 20 minutes. So this is the latency. What is the throughput? If you remember, we said the throughput is the number of units or tokens that are being produced per unit of time. So since each unit takes 20 minutes, we can just consider the unit of time to be, let's say, 1 hour. So in this case, the throughput would be 1 hour divided by 20 minutes per cookies. So it's going to be 3 trays per hour. So that is the throughput for the system that Ben is going to design. So without any sort of parallelism. So now let's just say we want to either use a spatial parallelism or temporal parallelism. So what is the latency and throughput if Ben uses parallelism? So for the spatial parallelism, he uses his friend to help. So basically his friend uses her own oven. So that is an example of spatial parallelism. On the other hand, when we have, let's say, two stages, one other option is that we can either use more trays or we do some of the work simultaneously as well. So that is an example of temporal parallelism too. So let's just see how these different scenarios help us increase throughput. So for the first scenario, spatial parallelism, we have two ovens. So Ben and Alyssa, they work simultaneously. So since we have two stages for baking cookies, we can have Ben roll the cookies and then bake them in his oven, and Alyssa does the same in her oven, right? So what is the latency for each tray now? So each tray, it still takes 20 minutes to be prepared because we still need 5 minutes for rolling the cookies and 15 minutes for baking them. So it will be still 20 minutes as for the latency. However, since now we have two baking stages and each one can bake 3 trays per hour, now we have 6 trays per hour as for the throughput for this baking procedure. So as you can see, using a spatial parallelism, we were able to increase the throughput. Now let's just take a look at one example of using temporal parallelism. Let's see how would that work. So for this example, we first roll the cookies, we start to bake. While these cookies are being baked, we roll the second batch too. So even though we have to wait for the first batch to be ready, but still, since we rolled the cookies simultaneously, we were able to increase the throughput. So let's just see by how much. So again, what is the latency for baking cookies? It's still the same, because for each batch of cookies we have 5 minutes to roll and we have 15 minutes to bake. So this didn't change. Remember, latency is the time that takes per each token, or for our example, for each tray, right? So this time hasn't changed. But what has changed is that now, except for the first one, since we didn't have any rolled cookie batches, right? For the second, the third, until to the last one, we only need to spend 15 minutes, because rolling of the cookies and baking happens at the same time. So here we roll the second batch while the first batch is being baked. So because of that, the amount of time that it takes, or the number of trays that we can bake per hour, increases. So here we can bake 4 trays per hour. Why? Because again, while we wait for the one to bake, we roll the other one. So if we start from this 5 minutes and then we go until the 65 minutes, we see that we were able to bake 4 trays of cookie per hour. So by doing temporal parallelism, we were able to increase the throughput as well. So now let's say we combine these two techniques. Not only we do the spatial parallelism, so we use 2 ovens, but also we use the temporal parallelism too. So we roll the cookies while the previous batch is baking. So by combining the two, we can double the throughput from 4 trays per hour to 8 trays per hour. Of course, as you can see, these were very basic examples, but they can serve as a good gateway for you if you are interested in this topic to go and look for it on your own.